Alright, welcome back. This is the last part of this tutorial. So far, we've gone through 1, we've gone through 2. You can find this in the videos in the playlist. And now we're gonna go through 3, which is to populate the skeleton with the Kalman filter code and make sure that the tests pass. Here, I have the code that we've been working on. If I go to Python, let me source the virtual environment. Remember that if I do PyTest, I get failing tests, and those are the C++ tests that are failing. So what we have to do is to populate the code in the skeleton in C++ so that these tests will pass and our C++ implementation will be complete. What I'll do is I'm going to open Visual Studio Code. On one hand, well, let me close this that I won't need anymore. So we have this on one hand that is going to contain our Kalman filter code that we want to then now port to C++. And I'm going to go to cpp build and call Qt Creator here. Okay, so if we go again to our KF Kalman filter code, this looks too big. Maybe let's do something like that. Then remember, we have to fill in our constructor, predict, and update functions. And so far, if we run, let me open another terminal here. If I run PyTest, you can see that there are 4 tests failing for the C++ and 4 that are passing. So let's make 1 test pass at a time. So the simplest test that we have is that it can construct and return the position and velocity. So let's work through this one first because that seems to be the easiest. So we definitely need to be able to use these values that right now are not being used at all. And furthermore, remember that we're returning the covariance, mean, and position. And right now, these are constants. So what I'm going to do is first define some private variables. And here, remember this type matrix is a 2x2 matrix here, right here. So what we need in the state vector is have a 2D vector and a 2x2 matrix. So what we'll do here is say vector M mean, matrix M covariance. And the idea is that this has to be initialized according to this. And for that, we're going to go to the Python code. Here we have code. So what we'll do first is say mean set 0 to replicate this code here. In Python, we have numvars because the NumPy array is dynamic in size, can take any shape. However, here, because we use fixed matrix sizes and vector sizes, then there's no need to specify the size at this point. And we're gonna do, actually, that this doesn't make much sense, but let's do it. So the ix equals initial x and mean iv equals initial v. And one thing we need to do further is static const int ix equals 0, static const int yv equals 0. If you hear some noise, it's my neighbors walking on the floor above. All right, so we could get rid of that. So that initializes our state vector. We need to save the acceleration variance and initialize the covariance matrix to an identity. So here we will do m covariance set identity, and we need to save the acceleration variance. So for that, I'm going to use the const variable. So because we know that this is not going to change over the lifetime of our Kalman filter class. So mxl variance, and we're going to go define this one as const double below here. And to me, this is very useful because whatever is constant throughout the lifetime of an object should be labeled as const. And in this case, we are constrained to initialize it here in the constructor. All right. This format. Okay, let's do it like that. All right, so this so far is going to be able to construct the object. Furthermore, we need to here return m covariance. Here return m mean. Note that here I'm returning a copy on purpose so that no one can modify my internal state. But if this matrix or vector were to be very large, then it would be worth returning a const reference. And finally, the position, we're going to return m mean ix and the velocity m mean iv. Okay. So here we filled everything except predict and update. So this means that at least one test, specifically this one, should now pass. Let's see. We need to compile, of course. So I'm going to build from here. You can also build from the command line. Compile output. Okay. Done. PyTest. It's still failing. Why? Oh, yes, so I messed up. This is why the tests are useful. So, yes, this is a problem. IV should be 1. Might be better to use an enum for that. But this shows you why having tests is useful. That was caught straight away. Hoo, yay! So only 3 failed. So now 5 passed. Great. So this is working. Now for the other tests to pass, there are 2 things. This one is testing predict, and there's one testing update. So what we need to do here in predict is the code that is here. In this case, we need an F matrix. That is going to be also 2 by 2, so I can use the same. Yeah. Let's make it identity initially. F ix iv equals t. Basically, that's everything we need. And we will have vector new x equals f multiplied by m mean. So that's pretty convenient. Sorry, here I didn't follow the same notation. Very bad. I should have done that. But well, let's continue. Here you see that because here we have vector and matrices in eigen, we can use the asterisk for matrix multiplication, and there's no need to have something like dot in NumPy. That's very convenient in this case. So that's going to be the new x, and I'm going to make it const here. And we need to have g, which is going to be, in this case, that's a bit more complicated, but no, because actually it's a vector. So vector g ix equals 0.5 multiplied by dt, and giv equals dt. And new p equals, and here we have, let's copy paste it here for now so it's easier for me to new p is f multiplied by the previous p by f plus g dot g transpose multiplied by the acceleration variance. Okay, so that's new p. And finally we say that actually covariance equals new p and mean equals new x. All right, let's build this first. Okay. Yay! It's passing. So now only 2 tests are failing. Haha, not necessarily. This one is failing, actually. And it is because, yeah, I'm sending keyword arguments. This is something I didn't fix in the previous video. And this is because if I go to the tests, yes, but. So I think that should. Yoo-hoo! Only 1 test failing, unless it's a test for the update. One comment before I proceed is that this might be a waste of code and time. There's probably a more efficient way to write this. However, I'm leaving it like that because we are still prototyping and things might fail, but later it could be optimized further. That's to be discussed because these matrix and vector objects are of fixed size, and Eigen is doing a lot of optimizations, so actually we might not be losing much performance here. And we gain clarity in our code. All right, update. So now we have to replicate this code in C++. So we have here that h is, well, this is a particular shape because it's 1 by 2. So for that, we're gonna define matrix double 1 by 2. Actually, 2 is numbers, right? Yes, numbers. h z0 in case h0 ix equals 1. Here we have a 1 element value, so I'm going to use directly double and not matrices. And we have that y is z minus h dot dat. Z, which is measurement value, minus h multiplied by m mean, and s equals h dot covariance multiplied by h transpose plus measurement variance. And this can also be a double. Let me see if this compiles so far, because I'm a bit afraid of these conversions from matrices to a single scalar. All right. So we're almost there. Now K is the Kalman gain, and it's going to be a vector of 2 by 1, and it's going to be mcov multiplied by a transpose multiplied by the inverse of s. Okay, and now for now I'm going to put s, but we have to compute the inverse. I think, I don't remember if something like this works. And vector new x equals m mean plus k dot multiply by y. This was k. And matrix new p equals matrix identity minus k multiplied by h multiplied by mcov, and mcov equals new p, m mean equals new x. Yes, there's no env. This is very bad. Actually, yes, of course, it's the double, it's not a matrix. Yeah. There we should check that S is not 0, for example. Or more than 0 in the number, because it won't be 0 as long as measurement variance is not 0 and the rest is appropriate. Ooh, the tests are passing. Good. So now the tests are passing. I could beautify this code a bit further. For example, I don't like that here I called it X and here it's covariance, because then we start to be out of sync between the two, the Python and the C++ implementation. And what I would like to have when I do this is that I can prototype in Python and then move to C++, and that the code is kept synchronized and as similar as possible. And in this stream of thought, there is one more thing that we would like to do to make sure that both implementations do the same. And that is that so far, nothing is telling us that predict and update are doing exactly the same in both implementations. Because in this test, we have, okay, update decreases the state uncertainty and predict increases state uncertainty. But by how much and what's the resulting state? That's what we don't know. And therefore, for example, we might in the predict function here add 0.1, and the tests are going to pass, all of them. But actually, the Python and the C++ implementation are not doing the same thing. So we need one more test. And I would probably use it, make it a different, let me sort of copy this. And I'm going to make it a different fixture because it's not a parameterized test. So we can do test kf Python and CPP yield same results. Test yield same results with predict. So that's very important. So we can, for example, I will remove this. I'm going to keep that test. There's a kf Python equals Python kf.kf, and then we're going to have also kf cpp equals cpp kf.kf. So we create the same one, and now remove this. We're going to do the same to both. And we want to self-assert true NP all close. So we want that the covariance and the mean are close. So kfpi.cov kfcpp.cov are equal up to, let's say, 10 to the minus 4. And that the means are also close enough. And if we run the tests, then we see that the covariance matrices don't match. So there's something going on there. Well, let's see if we comment the covariance matrices if the mean is working. Yes, okay, that's being computed correctly or in the same way in both Python and C++. So what's happening is with the covariance matrix, and that is exactly has to do with this line and these matrices, and comparing the code. It seems to be that I forgot something. Yeah, and it is this. So it's FP, F transpose, and here I forgot transpose. So let's build again. That's the power of tests. Otherwise, we would have detected that much later, probably. So now if we run again, yoo-hoo, it's passing. And what I would do typically is to push also this as much as I can to make sure that these tests are very sensitive to whatever is going on. So yeah, there we go. Now one more test. This is not gonna be this name, but yield same results with update. So same as before, we're gonna do was it? Yeah, that's probably okay. So we create the 2, and after we do update, we should have the same covariance, and okay, there we go. Okay. I forgot, yes. KFCPP. KF pi. Woohoo! All right, so the only bug we had here was the one that was computing the covariance matrix incorrectly because it was missing a transpose operation. All right, that ends this tutorial and the playlist. I hope you liked it. Leave me any comments if you would like some topics to be addressed or what you think. I'm happy to get some feedback. And maybe I'm gonna do more videos later, beautifying a bit the code, making it safer. As future work or things that can be done to improve the code, here I would very carefully check that these P and X, that these are not none or infinity, otherwise do something about that. I would not have a division like this over something that can be 0, things that could give us a large headache later on. All right, hope you liked it, and until the next video.